Hello, and welcome to Late Physics, where we dive deep into the mysteries of the universe. If you're fascinated by the cosmos, the nature of time, or just love exploring the unknown, you're in the right place. Before we journey through the fascinating world of time, be sure to hit that like button, subscribe, and join the conversation by commenting below. And by the way, where are you watching or listening from? Whether you're in the quiet of your own home or gazing at the stars from your favourite spot, time has a way of shaping your experience, much like it shapes our entire universe. Today, we're about to unravel one of the greatest mysteries of all. Why does time only move forward? Have you ever wondered why we can't rewind or skip ahead? Why the past is behind us and the future seems always just out of reach? You might think of time as a constant flow, but there's more to it than meets the eye. From ancient philosophy to modern physics, from the Big Bang to the far future of our universe, time has captivated and confused humanity for centuries. Stay with us as we explore how time moves, what controls its direction, and whether we could ever understand or change the way it flows. Buckle up, because the journey through time's many layers is about to begin. Time is something we experience every moment of our lives, yet when we stop to think about it, it quickly becomes a bit of a mystery. It's a feeling that time is constantly moving forward, unyielding and inevitable. We set our clocks, we plan our days, and we live by the ticking of the seconds, minutes, and hours. In many ways, time feels simple. It feels like a linear force that carries us from one moment to the next, from the past to the future, without pause. And yet, despite its omnipresence, time has puzzled philosophers, physicists, and thinkers for centuries. For most of us, the passage of time is something so natural we hardly think about it. We mark it by birthdays, anniversaries, and the rhythm of our daily routines. But when we step back and truly consider what time is, we realize how strange it is. After all, in the world of physics, time doesn't seem as straightforward as it feels in our daily lives. While we experience time as a steady, one-way journey, scientific laws do not always point in the same direction. In fact, time may not be the simple, unidirectional force we intuitively think it is. Some physicists argue that time's flow isn't as constant as it appears, and its direction might not always be so clearly defined. This leads us to wonder, could time be more complex than we assume? Could there be ways in which time behaves differently under certain conditions or in certain places in the universe? Is time really only moving forward, or are there other possibilities we've yet to fully understand? The pursuit of answers to these questions has led to some fascinating theories. Some of these ideas are groundbreaking and even a bit unconventional. There are theories that suggest time might be cyclical, looping endlessly, rather than moving only forward. Others propose that time may not even be fundamental at all. It could be a product of our minds, a way of making sense of a universe that doesn't inherently care about time. Theories like these push us to rethink how we view the very nature of time and the universe we live in. As we venture into this topic, we will explore the relationship between time, the laws of physics, and the structure of our universe. We will examine how the concept of time influences not just the way we think about the world, but also how the world itself works. From the moment the universe began with the Big Bang, time has played a key role in shaping everything from the formation of galaxies to the evolution of life on Earth. And yet, time is not just something we measure with clocks or calendars. Time is also a force that shapes the very fabric of reality. It's central to the laws of physics, from the fundamental principles of relativity to the mysterious flow of entropy that governs the universe. Time has a deep connection to how things change, from the tiniest subatomic particles to the largest structures in the cosmos. Understanding time is key to understanding the laws that govern everything in existence. But what if some of the ideas we have about time are incomplete or even wrong? In recent years, new scientific theories are emerging that challenge the way we've traditionally thought about time. These new theories could reshape our understanding of everything from quantum mechanics to the nature of the universe itself. Some physicists argue that time could be an illusion, something that doesn't truly exist in the way we think it does. Others are investigating whether time might not flow in a single direction, and whether it might be reversible under certain conditions. In today's exploration, we're going to dive deep into these ideas. We'll uncover how time might not just be a simple flow from past to future, but a more intricate force that ties together the laws of physics, the evolution of the universe, and even our own experience of life. By looking at the work of physicists and philosophers, from Einstein to more recent thinkers, we'll try to uncover what time really is, why it behaves the way it does, and what that might mean for the future of science and our understanding of reality. So, sit back and relax as we begin this journey through the mystery of time, one that stretches back billions of years and yet is still unfolding before our very eyes. When we think about time, we often think of it as a universal constant, a ticking clock that measures the passing moments of our lives. But what if time isn't just something that happens around us? What if it's also something deeply tied to the very nature of our consciousness, the way we experience ourselves and the world? This idea begins to suggest that time might not only be a feature of the universe, but also a key component of how we perceive reality itself. One fascinating perspective on time comes from Rodolfo Linas, a neuroscientist whose work has focused on understanding the brain and its connection to our awareness of time. Linas proposed that our perception of time arises from neural oscillations, rhythmic patterns of electrical activity in the brain. These oscillations, which occur across different regions of the brain, help coordinate the flow of information and give rise to the subjective experience of time. In essence, our brain seems to measure time through these internal rhythms, and it is through these patterns that we come to understand the passage of time in our lives. But this theory raises some intriguing questions. If time is so deeply rooted in the structure of our brain, then does it mean that our experience of time is a product of the brain's functioning? Is time, as we understand it, something that emerges from the intricate web of neural activity in our minds, rather than a fundamental property of the world around us? It's a complex idea, and it suggests that our sense of time might be a mental construct, one that depends not just on the outside world, but on the brain's internal processes. Another key figure in the study of time and consciousness is Antonio Damasio, a neuroscientist who has made significant contributions to our understanding of the relationship between self-awareness and the perception of time. Damasio's work suggests that the brain creates a sense of time within the context of self-awareness, the ability to recognize oneself as a distinct entity in space and time. This sense of time isn't something that's just given to us by the external world. Rather, it emerges from our brain's ability to reflect on our experiences and maintain a continuous sense of self. Damasio argues that our sense of time is intimately connected to our ability to remember. Memory is not just about recalling facts and events, it's also about experiencing time. Our memories allow us to stitch together the past, present, and future, creating a coherent narrative of our lives. Without this memory, time would feel fragmented, disconnected. The past would be lost and the future would remain a distant uncertainty. This continuity is essential to our sense of being. According to Damasio, this internal sense of time is what gives rise to our experience of being in the world, moving through it and interacting with it. Our brain, through its intricate neural networks, gives us the ability to anticipate the future, reflect on the past, and experience the present, all as parts of a continuous flow. In this way, our consciousness of time is a reflection of how our brains process information and construct a sense of self over time. This brings us to a theory known as the timeless brain hypothesis, which adds an interesting twist to the idea of time's connection to consciousness. This theory proposes that the brain itself is, in a sense, timeless. The brain doesn't actually experience time in the way we think it does. Instead, the passage of time, our experience of it, is something that emerges from how the brain processes information. According to this hypothesis, time is a construct of perception, not something inherent to the brain itself. In this view, time doesn't exist as an intrinsic feature of the brain's operations. Rather, it arises from the way the brain creates and organizes memories. These memories are then linked together in a continuous stream, giving us the illusion that time is flowing forward, from the past through the present and into the future. In a sense, it's the brain's ability to store information and then bring it to mind when needed that generates the feeling of time moving forward. This ties back to Damasio's ideas, where memory is not only how we recall past events, but also how we experience the continuity of time. The timeless brain hypothesis suggests that we experience time because of how our brains process and store events. The brain's neural systems constantly take in new information, store it, and recall it in ways that allow us to orient ourselves in time. The flow of time we feel is, in a sense, a construct of our memory systems. What we perceive as the passage of time is really our brain's ongoing activity of moving information through its networks, creating a narrative that spans from our past experiences to our present state and toward what we imagine might come next. This brings us to a crucial point. Our memory is not just about past events, but about how we project the future. The brain doesn't merely store a static snapshot of past experiences, it uses that information to form expectations about the future. This is how we plan, how we anticipate, and how we feel the continuous flow of time moving forward. Without this ability to project the future based on past experiences, our sense of time would be incomplete, leaving us trapped in a fragmented, disjointed present. What's even more intriguing is that these processes aren't just limited to human beings. Other animals experience time differently, depending on how their brains process information. Some animals, like certain species of birds, are able to form memories that span years, allowing them to track time in ways that are vastly different from how we experience it. Studies in cognitive science show that some animals may have a more acute sense of time in specific contexts, like migration or hunting, where precise timing is critical. These differences in time perception highlight the flexibility of the brain's time processing mechanisms. The study of time and consciousness is still in its infancy, and scientists are continuously exploring how different cognitive systems create our experience of time. But one thing is clear: time is not just a passive measurement of the world around us. It is intricately tied to the workings of our mind, to how we remember, anticipate, and ultimately experience the flow of life. Emerging research suggests that by better understanding the neural mechanisms behind time perception, we might unlock new ways of thinking about consciousness itself. We might also gain new insights into disorders that affect the perception of time, such as dementia or schizophrenia, where individuals experience time in radically different ways. If time is indeed a product of the brain's inner workings, then studying these mechanisms could provide us with a deeper understanding of both time and the mind. As we continue to explore time's connection to consciousness, we'll uncover more about how our brains shape the very nature of our experience. Whether it's through our perception of the past, our sense of the present, or our anticipation of the future, time remains one of the most fundamental aspects of what it means to be conscious and aware. The concept of entropy is one of the most intriguing and important ideas in the study of time. In essence, entropy measures the level of disorder or randomness in a system. It tells us how spread out energy is and how much energy is unavailable for doing work. In simple terms, it's the tendency of systems to move toward greater disorder. This notion is central to the second law of thermodynamics, which states that in an isolated system, entropy will always increase over time. The second law of thermodynamics provides us with one of the clearest glimpses into the forward movement of time, suggesting that time has an inherent direction, toward more disorder, toward more entropy. But, as we dig deeper, we find that this process may not be as straightforward as it first seems. Erwin Schrödinger, one of the founders of quantum mechanics, introduced a fascinating idea related to entropy in his 1944 book, What is Life? He proposed that living organisms seem to defy the overall trend toward increased entropy. Schrödinger coined the term negentropy to describe the apparent ability of living systems to decrease their internal entropy by maintaining a state of order. While everything in the universe tends toward disorder, living organisms are capable of harnessing energy in such a way that they maintain a highly ordered, low-entropy state. This ability to resist the natural tendency toward chaos is one of the defining features of life itself. By using energy from the environment through processes like metabolism, living systems can reduce their internal entropy, creating and sustaining the complex structures that make life possible. However, this ability to maintain order comes with a catch. The overall system, which includes the organism and its environment, is still subject to the second law of thermodynamics. While a living organism might maintain order internally, it does so at the cost of increasing entropy in its surroundings. For example, when we eat, we break down food into simpler molecules, releasing energy in the form of heat, which spreads out into the environment. In this way, while we might momentarily reduce entropy within our cells, the total entropy of the universe still increases. This interplay between life's ability to resist disorder and the relentless increase in overall entropy brings us to one of the most fascinating aspects of time's arrow, the directionality of time itself. Entropy gives us a clear, observable sign of the flow of time. The universe, as a whole, moves toward increasing entropy. We see it in everything, from the gradual cooling of stars to the spreading of heat in a cup of tea. Time, it seems, is always moving forward, driven by the relentless tendency toward greater disorder. But what if time's arrow is not as fixed as we think? What if it could be reset, or even reversed under the right conditions? This is where the ideas of Roger Penrose come in. Penrose, a renowned theoretical physicist, proposed a thought-provoking concept known as conformal cyclic cosmology. This theory suggests that the arrow of time may not be as unidirectional as we have long assumed. According to Penrose, the universe could go through cycles of expansion and contraction, with each cycle beginning with a big bang and eventually ending in a state of maximum entropy, often referred to as heat death. After each cycle, the universe would reset, and time would start over again, essentially erasing the past and beginning a new cycle from scratch. This idea challenges our traditional understanding of time as linear, flowing from past to present to future. Instead, Penrose's theory suggests that time might be cyclical, resetting after each cosmic epoch, with the arrow of time pointing in a new direction each time. This could mean that the universe goes through infinite cycles, each one starting with a big bang and ending in a state of maximum entropy before beginning again. It's a fascinating thought, and one that invites us to reconsider everything we know about time, the universe, and the very nature of existence. But there's another layer to the connection between entropy and time's flow, and it comes from the work of Ilya Prigogine, a Nobel Prize-winning physicist. Prigogine's theory of dissipative structures offers a new way of thinking about how systems can create order and structure, even as they increase in entropy. Prigogine argued that systems far from equilibrium, such as living organisms, weather patterns, and even the cosmos itself, can spontaneously organize themselves into complex structures. These structures, which we see as patterns or forms, arise from the very forces that lead to entropy. Dissipative structures are systems that dissipate energy in such a way that they create organized patterns or structures. This process, which appears to go against the typical trend toward disorder, is crucial in understanding how life and complexity emerge in the universe. In this view, time's forward movement isn't just about increasing disorder, it's also about the potential for new forms of order to emerge, even in the face of increasing entropy. The classic example of a dissipative structure is a whirlpool. When water flows in a circular pattern, it creates a structure that is organized, despite the underlying increase in entropy. In living organisms, this principle is even more evident. The organization of molecules into complex self-replicating systems like DNA represents an example of how dissipative structures function in nature. These systems don't violate the second law of thermodynamics. Rather, they demonstrate how, under the right conditions, the forces of entropy can give rise to new patterns and forms. This view of time is far from the simplistic model, where entropy just increases in a linear fashion. Instead, it opens up a more complex picture of time, one where new forms of order and complexity can emerge, even in the face of increasing entropy. Time, in this sense, becomes a dance between disorder and order, between the inevitable rise of entropy and the creation of new structures that give rise to the complexity of life itself. To further deepen our understanding of entropy and time's directionality, we need to consider how entropy might manifest in ways that challenge our usual perceptions. For example, consider the possibility that, on a quantum level, time might not behave in the predictable, irreversible way we think of at macroscopic scales. In quantum mechanics, particles can behave in ways that seem to defy the classical understanding of time. Some quantum systems are described by what is known as time-symmetric dynamics, where the equations that govern their behavior don't distinguish between the past and the future. In other words, time might appear to be reversible at the smaller scales, with particles following paths that could theoretically be reversed without breaking any physical laws. However, the overall picture still remains consistent with the second law of thermodynamics. The universe as a whole tends toward greater disorder. While the micro-world of quantum mechanics may allow for the possibility of time's reversal in specific situations, the macroscopic world, the world we experience every day, continues to follow the inevitable path toward increasing entropy. These ideas push us to rethink time in profound ways. Time isn't just a simple linear progression from one moment to the next. It's a dynamic and multifaceted concept, deeply tied to the fabric of the universe. From the increase of entropy in the cosmos to the self-organizing patterns of living systems, time's flow is far more complex than we typically imagine. As we continue to explore these connections, we find that time is not just a force that moves forward. It is also a force that shapes the very nature of existence itself, from the smallest particles to the grandest cosmic cycles. The mystery of time is not just in how it flows, it's in how it creates, how it organizes, and how it gives rise to the complexity we see in the universe around us. The concept of the arrow of time is one of the most fascinating and fundamental ideas in our understanding of the universe. Time, as we experience it, is a one-way journey, always moving forward from the past through the present and into the future. But how does this flow of time relate to the larger-scale processes of the universe? How do the fundamental laws of physics, such as the second law of thermodynamics, tie into the evolution of the cosmos, guiding it toward a future shaped by increasing entropy? The most striking evidence of the arrow of time at the cosmic scale is the ongoing expansion of the universe. The universe, since the Big Bang, has been growing in size, with galaxies moving farther apart from one another as time passes. This expansion is not just a curiosity, it's a crucial indicator of how time moves in one direction. To understand this better, we need to grasp what it means for the universe to be expanding. The discovery of cosmic expansion, which began with Edwin Hubble's observations in the early 20th century, showed that distant galaxies are moving away from us, and the farther they are, the faster they appear to be receding. This phenomenon is not due to galaxies moving through space, but rather because space itself is expanding. This means that the very fabric of space-time is stretching, pulling galaxies apart and increasing the distance between them over time. This expansion is a direct manifestation of the passage of time. The observable universe today is vastly larger than it was just a few billion years ago, and as time progresses, it will continue to grow. The expansion of space has profound implications for our understanding of time. It tells us that time is not simply a static, unchanging backdrop against which events unfold. Instead, time is intrinsically linked to the fabric of the universe itself. As the universe expands, time moves forward, and we witness this progression in the way galaxies drift further apart. This expansion is not reversible. It's an irreversible process, much like the flow of time itself. Just as we can't turn back the clock, the universe cannot shrink back to its original size, nor can it return to a time when everything was compacted into a single point. The arrow of time and the expansion of the universe go hand in hand, both moving in one direction. This ties directly into the second law of thermodynamics, which states that the total entropy of an isolated system will always increase over time. Entropy, as we discussed earlier, is a measure of disorder or randomness. In a more ordered system, like a freshly organized room, entropy is low, but as time progresses, things become disorganized, and entropy increases. In the case of the universe, the second law of thermodynamics ensures that as it expands, entropy continues to increase. As galaxies move farther apart, the energy in the universe spreads out, becoming more diffuse. This spreading out of energy is a manifestation of increasing entropy, and it drives the universe toward a state of greater disorder, or equilibrium, where no more work can be done. The connection between the expansion of the universe and entropy is what gives time its arrow. The universe is constantly evolving, driven by the forces of entropy, and this evolution is irreversible. The galaxies are not just moving away from each other, they're also becoming more spread out in terms of energy and matter. This increasing dispersion leads to a less structured universe, filled with more randomness and less potential for complex interactions. The direction of time is essentially tied to this progression, toward a universe that is cooler, more uniform, and filled with higher entropy. One of the most profound consequences of this process is the eventual fate of the universe. According to our current understanding, as the universe continues to expand and entropy increases, it will eventually reach a state known as heat death. This is the point at which the universe will be in thermodynamic equilibrium, with no differences in temperature or energy available to do work. In other words, all processes will cease, and the universe will be in a state of maximum entropy, where nothing can change or evolve. This scenario represents the ultimate end of the arrow of time, when time itself may no longer have any meaningful progression, as everything will have reached a state of stasis. But could there be a different fate for the universe, one in which the arrow of time is reset or reversed? This is where the ideas of physicists like Roger Penrose come into play. Penrose proposed a theory called conformal cyclic cosmology, in which the universe goes through an infinite series of cycles, with each cycle beginning with a Big Bang and ending in a state of maximum entropy, known as heat death. According to Penrose, once the universe reaches heat death, time doesn't simply stop. Instead, it starts over again in a new cycle, with a new Big Bang. Penrose's theory suggests that time itself could be cyclical rather than linear. Rather than moving from past to future in a single, irreversible flow, time could reset after each cosmic cycle, starting anew with each expansion. In this model, the universe would not simply end in heat death. It would experience a rebirth, beginning the process of expansion once again, with new cycles of entropy, time, and cosmic evolution. This idea challenges the traditional view of time as a one-way progression and offers an intriguing possibility. The universe, and the flow of time within it, could be part of an eternal cycle of birth, death, and rebirth. While Penrose's cyclical model is a fascinating alternative to the standard view of the universe's fate, it remains speculative. The theory is not without its challenges, particularly when it comes to the detailed mechanics of how time could reset in such a way. However, it underscores a deeper truth about the universe and the nature of time, that time might not be as simple as a line stretching from past to future, but rather something far more complex, tied to the fundamental workings of the cosmos itself. Another important perspective on time's direction comes from the work of Carlo Rovelli, a physicist who has made significant contributions to the field of quantum gravity. Rovelli has suggested that time, at the fundamental level, might not exist at all. In his view, time is not a fundamental feature of the universe. Instead, it emerges from the relationships between events in space. In this approach, time is a construct that arises from the way things interact, rather than being a universal backdrop against which events unfold. This idea challenges the very foundation of how we think about time, and opens up the possibility that time's flow might not be as fixed or inevitable as we've traditionally believed. According to Rovelli's theory, the concept of time might be a product of our perspective, a result of the way we perceive changes in the universe. This idea is rooted in the field of quantum mechanics, where time itself doesn't always behave as we expect. At the quantum level, particles can exist in superposition, existing in multiple states at once, and time seems to blur in ways that don't fit neatly into our classical understanding. In Rovelli's view, time emerges from these quantum interactions, and its flow may not be as absolute as we once thought. This view of time as an emergent property of the universe's interactions aligns with the growing realization that time, rather than being a fixed external force, may be deeply intertwined with the very fabric of reality itself. If time is indeed an emergent phenomenon, its flow may be shaped by the interactions between particles, energy, and gravity, rather than being a simple linear progression. This brings us back to the idea of time as a dynamic, evolving feature of the universe, one that is tied to the fundamental laws that govern the cosmos. The direction of time, from the cosmic scale of expansion to the microscopic level of quantum mechanics, remains one of the most profound and mysterious aspects of our understanding of the universe. Whether time is a linear, unidirectional force driven by entropy, a cyclical phenomenon governed by the universe's cycles of birth and death, or an emergent property of quantum interactions, it is clear that time is deeply connected to the evolution of the cosmos. As we continue to explore the arrow of time, we discover not only how the universe has evolved, but also how the very nature of time itself shapes the way we experience reality. Causality is one of the most fundamental principles we use to understand the universe around us. At its core, causality is the idea that events don't just happen randomly, they occur in a particular order. For every effect, there is a cause, and that cause happens first, followed by its effect. This simple yet powerful concept is deeply intertwined with our understanding of time and how it moves forward. Without causality, the passage of time would be meaningless, for time itself is defined by the sequence of causes leading to effects. We experience causality in our everyday lives. If you drop a glass, it falls and shatters. The cause, the act of releasing the glass, leads to the effect, the glass falling and breaking. Similarly, the weather changes due to complex interactions in the atmosphere, and the choices we make lead to different outcomes in our lives. But causality is not just a practical concept, it's a cornerstone of both classical and modern physics, offering us a way to make sense of the natural world and how events unfold across time. In classical physics, causality was understood as a fundamental and absolute principle, with the universe behaving in a predictable and deterministic way. Sir Isaac Newton, in the 17th century, provided a clear framework for how objects move and interact through forces, all of which could be traced back to their causes. If we knew the initial conditions of a system, such as the position and velocity of every particle, we could predict the future state of that system with complete certainty. This is what we call determinism. It was assumed that if we understood the causes, we could predict the effects, and the universe would unfold like a giant clockwork mechanism, moving forward step by step in a precise, predictable manner. However, this classical understanding of causality was radically altered by Albert Einstein in the early 20th century, particularly with his theory of special relativity. Einstein's work revolutionized how we think about time, space, and causality itself. One of the key insights of special relativity is that the flow of time is not the same for all observers. Time is relative, meaning it depends on the observer's motion and the strength of gravity in their location. This realization led to a deeper understanding of how causality operates in the universe. In the context of special relativity, the idea of simultaneity, the concept that two events happening at the same time for one observer may not be simultaneous for another observer moving at a different speed, becomes crucial. Imagine two lightning bolts striking 2 points on a train platform. To an observer standing still on the platform, both strikes happen simultaneously. But to someone moving at a high speed along the platform, the lightning strikes might not appear to happen at the same time. This apparent contradiction doesn't violate causality because the order of events is preserved in both frames of reference. In other words, despite different observers experiencing time differently, the cause-effect relationship remains intact. The lightning strike that causes the flash of light is still seen to occur before any effect, such as the sensation of heat or the sound of thunder, can be experienced. Einstein's theory of general relativity takes this even further by explaining how gravity affects time itself. Massive objects, such as stars and planets, curve space-time around them, and this curvature affects the flow of time. Time runs slower near a massive object compared to an area of weaker gravity. This phenomenon, called gravitational time dilation, is another example of how time and causality are linked together, but in ways that defy our intuitive understanding. In the presence of a black hole, for example, time is stretched so much that, from a distant observer's point of view, an object falling into the black hole appears to freeze as it approaches the event horizon. The cause, the fall, happens, but the effect, the object reaching the event horizon, seems to be delayed, seemingly breaking the traditional cause-effect relationship. In reality, the cause is still happening in the object's frame of reference, but our perception of time in the presence of intense gravity is altered. As we dive into the quantum realm, the relationship between causality and time becomes even more mysterious. Quantum mechanics, which governs the behavior of the smallest particles in the universe, challenges our classical notions of causality. In the quantum world, particles do not have definite positions or velocities until they are measured. Instead, they exist in a superposition of all possible states. It's only when we observe a particle that it chooses a specific state. This behavior, famously demonstrated by the double-slit experiment, suggests that at the quantum level, causality isn't as clear-cut as we might think. The act of observation itself seems to play a role in determining the outcome, which is a striking departure from the classical idea of causality, where the effect follows the cause in a predictable way. This idea led to one of the most famous thought experiments in quantum mechanics, Schrödinger's cat. In this thought experiment, a cat is placed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the poison is released, killing the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of both alive and dead states. This paradox challenges our understanding of causality because, on one hand, the cause, the decay of the radioactive atom, should lead to a specific effect, the death of the cat. But until we observe it, the cat's fate is in a kind of limbo, existing in both states simultaneously. In the quantum world, causality seems to blur, and the act of measurement plays a crucial role in determining the outcome. Despite these strange quantum phenomena, causality remains foundational to our understanding of time in the macroscopic world. Even though quantum mechanics operates according to probabilities and uncertainties, the larger scale world, where everyday objects and forces operate, follows a much more predictable, causal structure. The fundamental laws of physics, like those governing motion and energy, still operate on principles of cause and effect. We can predict the trajectory of a rocket launched into space, or how the Earth will orbit the Sun, because the forces at play behave deterministically, in line with the classical understanding of causality. Causality also plays a crucial role in our philosophical understanding of free will and the nature of time. If every event is determined by a prior cause, does that mean everything is predestined? Or do we have the power to choose our own actions, breaking free from the chain of cause and effect? These are questions that have been pondered by philosophers for centuries, and while science can give us insight into how the universe operates, the question of whether we have true free will remains a deeply philosophical one. In a practical sense, causality is what allows us to make sense of the world around us. It's how we understand relationships between events, how we learn from our mistakes, and how we predict what might happen in the future. Whether we are applying it to the motion of planets, the behavior of atoms, or the choices we make in our daily lives, causality is the thread that connects the past to the present, and the present to the future. It gives time meaning and direction, guiding us through the unfolding events of the universe. Yet, as we've seen, the deeper we explore the nature of time, the more complex the relationship between cause and effect becomes. From the precise calculations of Newtonian physics to the mind-bending paradoxes of quantum mechanics, causality shapes our understanding of the universe in ways both straightforward and mysterious. As science continues to uncover the intricacies of the cosmos, we may yet discover new layers to causality that challenge our understanding even further. But for now, causality remains the bedrock of both time and space, the principle that allows the universe to unfold, one event after another. At the heart of quantum mechanics, time behaves in ways that challenge our classical understanding. While in our everyday lives we experience time as something steady, constant, and unidirectional, quantum mechanics suggests that time may not be so straightforward. In fact, some of the brightest minds in physics have proposed theories that radically rethink the nature of time, showing that it might be more complex and more mysterious than we've ever imagined. One of the most intriguing ideas comes from the physicist David Bohm, who proposed the notion of a holonomic universe. In Bohm's theory, time is not a linear, unchanging force, but a latent order, an underlying structure that only reveals itself as the universe unfolds. Imagine time not as a rigid progression of moments, but as something that is part of a deeper, more complex reality, something that we can only begin to understand as we observe the interactions within the universe. According to Bohm, this latent order is present in everything. It is a fundamental part of the quantum field that governs the entire cosmos. As the universe evolves, this deeper order gradually manifests in the form of events, actions, and interactions, what we perceive as the passage of time. In Bohm's holonomic view, time isn't just a feature of the universe, it's woven into the very fabric of reality, emerging as we experience the world. This is a radical departure from the way time is often thought of, as something separate, something that merely ticks away, unaffected by the events that occur within it. Instead, Bohm's theory suggests that time, much like space, is an intrinsic part of the universe's deeper structure. It is revealed gradually, not in a rigid linear flow, but in the way the universe unfolds, according to the quantum dynamics that govern all things. Bohm's ideas open up an entirely new way of thinking about time. If time is part of a latent order, then the seemingly random events we experience might be just a surface-level manifestation of something far deeper. It's as if time is both a process and a result, a structure that is always present but only reveals its true nature as the universe evolves. Another key figure in the exploration of time's role in quantum mechanics is Roger Penrose, who developed the concept of twistors. Penrose's twistors are a mathematical tool used to understand the structure of space-time, particularly in quantum mechanics. In the traditional view of space-time, we think of time as an independent flowing dimension, with the past, present, and future existing on a timeline. But twistors suggest that time may not be fundamental at all. Instead, time could be a higher-level manifestation of more complex relationships between the particles and forces that make up the universe. Penrose's work suggests that space-time itself is not just a static stage on which events unfold, but a dynamic, flexible structure that can bend and warp. Time, in this view, arises as a consequence of the relationships between particles and the geometry of space-time. In a way, time doesn't exist on its own. It emerges from the interactions of the universe's fundamental components. The concept of twistors provides a framework where time and space are not separate entities, but rather interconnected in a deeper, more unified way. This challenges the traditional view that time is an independent, unchanging backdrop against which events unfold. Instead, it suggests that time itself is an emergent property of a more complex underlying reality. Another physicist whose ideas challenge our conventional understanding of time is John Wheeler, who proposed the concept of the participatory universe. Wheeler's idea is a fascinating and somewhat mind-bending one. He suggested that the very nature of the universe depends on the presence of observers. In Wheeler's view, the universe doesn't simply exist independently of us, with time unfolding in a predictable way. Instead, the act of observation, of measuring and interacting with the universe, plays a key role in shaping reality itself. In other words, time and space do not simply exist as external realities, independent of our perception. Instead, they emerge through our interaction with the universe. This participatory view of the universe has profound implications for how we understand time. If time is fundamentally linked to the act of observation, then it's not a fixed, immutable dimension that passes regardless of who is observing it. Instead, time could be shaped by the very act of measurement, as the observer's choices influence how events unfold. In Wheeler's framework, the future isn't predetermined, but exists in a state of potential until it is measured or observed. This suggests that time could be more fluid, more interactive than we have traditionally thought. Wheeler's ideas lead us into deeper questions about the nature of time and the role of the observer. If the universe's unfolding is in some sense participatory, then could time itself be malleable? Are the events we experience as the flow of time shaped by our perception of them, or do they truly exist independent of us? These are the kinds of questions that Wheeler's ideas invite us to consider, as they open up new possibilities for understanding the relationship between consciousness, observation, and time. Adding another layer of complexity to our understanding of time is the work of Edward Witten, a leading figure in string theory. Witten's contributions to physics have helped shape our modern understanding of the quantum fabric of the universe. String theory proposes that the fundamental building blocks of reality are not point particles, as we once thought, but rather tiny, vibrating strings of energy. These strings exist in multiple dimensions, far beyond the familiar three dimensions of space and one of time that we experience. In string theory, time is not just another dimension in a four-dimensional space-time continuum. Instead, time may be part of a multi-dimensional structure that exists in higher dimensions. These extra dimensions, beyond the familiar ones we can perceive, influence how time behaves. The flow of time could be impacted by the interactions of strings in these higher dimensions, suggesting that time might not be the simple, linear phenomenon we experience in our everyday lives. If the fundamental forces of the universe are governed by string-like structures that exist in higher dimensional spaces, then our experience of time may be just one projection of a far more complex multi-dimensional reality. Witten's work suggests that time may not be a universal feature of reality, but something that emerges from the interactions between higher dimensional structures. If we think of time as part of the quantum fabric, shaped by the vibrations of strings in higher dimensions, then time itself may be more intricate, more interconnected with the rest of the universe than we ever thought possible. Finally, there is the many worlds interpretation of quantum mechanics, which provides yet another fascinating perspective on time. According to the many worlds theory, every time a quantum event occurs, the universe splits into multiple realities, each one representing a different outcome of that event. This suggests that time may unfold differently in each possible outcome, creating parallel universes that evolve independently, each with its own timeline. In this view, time is not a single linear progression. Instead, it is a branching, multi-dimensional structure where every possibility creates a new path. The future is not a single, inevitable sequence of events, but a complex network of potential outcomes, each of which could lead to its own version of time. This radically redefines our understanding of causality and the flow of time. suggesting that time itself is not a singular experience but a collection of multiple coexisting timelines. Each of these theories, whether it's Bohm's latent order, Penrose's twistors, Wheeler's participatory universe, Witten's string theory, or the many worlds interpretation, adds a layer of complexity to the way we think about time. They challenge our classical understanding and open up new possibilities for how time might behave at the quantum level. Time, it seems, is not a simple, straightforward force, but something far more mysterious, shaped by the very structure of the universe itself. As we continue to explore these ideas, we may uncover even deeper layers of reality, each one offering a new perspective on the nature of time and its role in the unfolding of the cosmos. The origins of time are one of the most profound and perplexing questions in science. What exactly marks the beginning of time? Is it tied to the moment of the Big Bang? Or could the concept of time itself be much more complicated than we've traditionally understood? To explore this, we need to consider some groundbreaking theories that challenge our usual perceptions of time and space. One of the most influential ideas in cosmology is Alan Guth's theory of cosmic inflation, which provides a radical answer to the early moments of the universe. According to Guth, shortly after the Big Bang, the universe underwent a period of rapid expansion, a phase in which space itself expanded exponentially faster than the speed of light. This inflationary period happened incredibly quickly, much faster than anything we can imagine. During this time, the universe stretched by an enormous factor in a fraction of a second, smoothing out any irregularities and setting the stage for the universe we see today. But what does this have to do with the beginning of time? Well, inflation suggests that time itself may not have had a well-defined meaning in the earliest moments of the universe. Before inflation, the universe was incredibly small, hot, and dense. So small that the laws of physics as we know them, including the very concept of time, might not have been applicable in the way we experience them today. In fact, some interpretations of inflation suggest that time as we know it could have only emerged once the universe expanded beyond a certain point after inflation began to slow down. In this sense, the Big Bang itself might not represent a definitive starting point for time. Instead, it marks a transition from a state where time, as we understand it, may not have existed to the time-filled universe we live in today. The expansion during inflation set the conditions for time to take on its familiar, forward-flowing character, one that we now experience every day. In this view, the birth of time isn't a simple event that happened once. It's tied to the evolution of the universe itself, a process that unfolded as the universe grew and cooled. This idea becomes even more intriguing when we look at Lee Smolin's theory of cosmological natural selection. Smolin, a theoretical physicist, proposed that the laws of physics, and even the nature of time, could evolve over cycles of cosmic birth and rebirth. In this model, the universe undergoes cycles of self-replication, where each cycle begins with a Big Bang, followed by a period of expansion and eventually contraction, leading to another Big Bang. Over time, these cycles could cause the laws of physics to evolve and adapt, with each new cycle giving rise to a slightly different version of the universe. What makes Smolin's theory especially fascinating is its suggestion that time itself could evolve through these cycles. If the laws governing the universe change with each new cycle, then time, along with space and the fundamental forces, might be subject to change too. In this way, time could be a dynamic and evolving feature of the universe, shaped not only by the processes that happen within it, but by the very structure of the universe itself. Smolin's work challenges the idea that time is a fixed, immutable property of the universe. Instead, it suggests that time may be something that evolves as the universe itself undergoes cycles of creation and destruction. This brings us to a broader question about the nature of time. Is time something fundamental that exists independently of the universe, or is it a property that emerges from the specific conditions of the universe? If time is indeed part of a cyclical process, its flow might not be as straightforward or as linear as we have come to believe. While Smolin's theory presents a cyclical view of time, another perspective comes from John Archibald Wheeler, one of the most influential physicists of the 20th century. Wheeler proposed a bold idea known as it from bit, which suggests that information is the fundamental building block of the universe. According to Wheeler, everything, space, time, matter, emerges from fundamental bits of information. This means that the universe is not made up of solid objects or particles in the traditional sense, but rather of information that gives rise to the structures we observe. In this framework, time is not an independent, absolute feature of the universe. Instead, it may be emergent, arising from the way information is processed and interacted with at the most fundamental level. Time, in this sense, could be a product of the interactions of information, a higher-level phenomenon that emerges from the flow of data between fundamental units of reality. In Wheeler's view, time is closely tied to the process of observation and measurement, because it is through the act of information being recorded and interpreted that time comes into being. This idea ties into the broader question of the nature of reality itself. If time and space emerge from the interaction of information, then time might not be as fixed or as universal as we think. It could be more subjective, more tied to the act of observation and the way the universe is experienced. This raises intriguing possibilities about the relationship between time and consciousness, whether time is a feature of the universe that exists independently of us, or whether it is something that emerges from the way we observe and interact with reality. Perhaps even more mind-boggling is the possibility that the very beginning of time itself, the Big Bang, might not be a true starting point. In some versions of cosmology, time could be more like a dimension that stretches across multiple regions of space-time, and the Big Bang represents a shift in how time is experienced, rather than the creation of time itself. This idea suggests that time could have existed in some form before the Big Bang, but the structure of time as we understand it today began at the moment of cosmic inflation. These questions lead us to broader metaphysical discussions about the nature of time. If time is not merely a linear progression from the past to the future, but something that can be shaped by the universe's structure and its evolution, what does that mean for our perception of reality? How do we reconcile the idea that time might be emergent or cyclical with our everyday experience of time as a forward-moving unidirectional force? Could time, as we know it, be a product of our minds, an interpretation of a deeper, more fundamental reality that we can't yet fully grasp? The idea that time might not be the fixed, linear force we assume it to be opens up a world of possibilities. If time can evolve, if it can change depending on the cosmic context, then our understanding of the universe itself is far from complete. We might be just beginning to scratch the surface of a much deeper and more complex understanding of time, one that ties together the origins of the universe, the evolution of life, and even the way we perceive the world around us. Time, in the end, may not be just a measure of the past, present, and future, but a dynamic, evolving feature of the universe, shaped by the very forces that govern everything from the smallest particles to the vastest galaxies. As we continue to explore these ideas, we begin to see that the beginning of time, far from being a singular event, might be an ongoing process, a process that shapes the universe and everything within it. Whether it's through cosmic inflation, cyclical creation and destruction, or the fundamental interplay of information, time's origins are deeply tied to the very structure of reality. And perhaps, in understanding time's true nature, we will uncover a deeper understanding of the universe itself. The idea of the end of time has long been a subject of both scientific inquiry and philosophical debate. Most people are familiar with the concept of heat death, the theory that the universe will eventually reach a state where all energy is evenly distributed and no work can be done. This state of maximum entropy, where everything becomes cold and lifeless, marks the ultimate end of the universe as we know it. But is heat death truly the final answer? Or is there more to the story? Could there be alternate endings to time itself? Or might time undergo a transformation we can't yet fully comprehend? Heat death, as it's commonly understood, is a direct consequence of the second law of thermodynamics, which states that in an isolated system, entropy, often described as disorder or randomness, always increases. As the universe expands, its energy spreads out and the temperature drops. Over billions of years, stars will burn out, galaxies will drift apart, and eventually everything will reach a state of thermodynamic equilibrium. In this scenario, there will be no more gradients of temperature or energy, and as a result, no processes can take place. Essentially, everything will come to a standstill with no events unfolding. Time, in a sense, would cease to have any meaningful direction or change. This vision of time's end, however, may not be as inevitable as it first appears. There are a number of theories that explore alternatives to this grim fate, each with its own imaginative take on the future of the universe and the nature of time. One such theory comes from Andre Linde, a leading cosmologist who developed the idea of eternal inflation. Linde's theory builds upon the standard model of cosmic inflation, which describes the rapid expansion of the universe just after the Big Bang. In eternal inflation, the expansion of space doesn't stop, it continues indefinitely. But here's the twist. As the universe expands, it spawns pocket universes, small, isolated regions where inflation ends and more traditional cosmological processes take place. Each of these pocket universes has its own unique laws of physics, and they may be completely separate from one another, creating an infinite multiverse. In this model, the end of time in our own universe might not be the end at all. While our universe may eventually reach heat death, the process of eternal inflation means that new pocket universes are constantly being created, each with its own timeline and potentially its own version of time. The multiverse theory suggests that time might never truly come to an end. It may continue in an endless cycle of creation, with new universes emerging, each with its own flow of time. From this perspective, the end of time in one universe doesn't spell the end of everything. It simply marks the closure of one chapter in a much larger cosmic narrative. Then there is Max Tegmark's mathematical universe hypothesis, which takes a very different approach to time's ultimate fate. Tegmark's hypothesis suggests that the universe itself is a mathematical structure. That is, it is governed by mathematical laws and can be described entirely in terms of mathematics. According to this view, time isn't a fundamental property of the universe in the way we usually think of it. Instead, time is a mathematical construct, emerging from the relationships between the various parts of the universe. This idea challenges the conventional view of time as an independent, flowing dimension. If time is just a construct, then it might not have a true beginning or end. Time could be a feature of the mathematical framework we use to describe reality, rather than an intrinsic part of the universe itself. In this sense, the end of time could simply be a shift in the way we understand the universe, a transition from one mathematical structure to another, rather than an irreversible decay into chaos or stasis. This theory suggests that time, like the laws that govern the universe, may be more flexible and contingent on the structures we use to understand it. Building on ideas of cosmic transformation and the nature of time, we can look at Frank J. Tipler's theory of the omega point. Tipler, a theoretical physicist, proposed a bold idea about the ultimate fate of the universe. He suggested that the universe will eventually collapse into a single point of infinite density, which he called the omega point. In this scenario, the entire universe's matter and energy will be drawn together, and time itself will reach a singularity, similar to the singularity at the center of a black hole, but on a cosmic scale. At this point, time could be reversed, and the universe might experience a kind of rebirth. In Tipler's omega point theory, the collapse of the universe doesn't mark its permanent death. Instead, it is the beginning of a new phase, one where time could potentially move backward or into a new direction altogether. This could mean that time doesn't follow a strictly linear path, with a finite beginning and an inevitable end, but rather could be part of a cyclical process, where time itself is reset. While this idea remains speculative, it offers an intriguing alternative to the concept of a one-way, irreversible march toward heat death. Even if we don't completely embrace the idea of time reversing or going in cycles, the notion that time might transform rather than cease opens up new ways of thinking about the ultimate fate of the universe. It suggests that time is not just an endless sequence of moments, but could be a feature that evolves, potentially taking on new forms as the universe changes. As we consider these alternative theories about the end of time, we must also entertain the idea that time's end might not be a final event at all. Instead, it could be a transition, a shift from one form of time to another, a passage from one state of the universe to the next. The end of time, in this sense, might not be a literal cessation, but a transformation into something entirely new. Theories like eternal inflation and the omega point suggest that time could be a much more dynamic, ever-evolving feature of the cosmos than we traditionally think. Perhaps the most profound implication of all these ideas is that time, far from being a simple one-way river from past to future, could be contingent upon the very structure of the universe. Time may not be a fixed, immutable force that flows in one direction, but something that can evolve, shift, and even be reborn, depending on the state of the cosmos. If the universe is constantly changing, through cycles of expansion and contraction, or through the emergence of new universes, then time might be just as malleable, subject to the forces that govern the universe's evolution. In the end, the question of time's ultimate fate is still very much an open one. While the theory of heat-death provides a grim yet widely accepted view of the universe's end, other theories, such as eternal inflation, the mathematical universe hypothesis, and Tipler's omega point, suggest that time could undergo a transformation rather than an absolute end. These theories offer us a glimpse into a future where time is not a singular, irreversible process, but a feature of the universe that evolves and changes, potentially in ways we can't yet fully grasp. Time, it seems, may not be a line that ends. It might be a cycle that continues to unfold, constantly reshaping the universe and itself in the process. Our experience of time is intricately linked to memory. When we think about time, we don't just experience it in a raw, abstract way, we experience it through our memories. Memory helps us stitch together the moments of our lives, creating a narrative of who we are and where we've been. It allows us to understand time as something more than a sequence of disconnected moments. It gives it meaning, structure, and continuity. The passage of time, in many ways, is inseparable from how we store and recall events. When we experience a moment, that moment doesn't just fade into the past, it is encoded in our brains, often in the form of memories. These memories act as markers of time, places where we can anchor ourselves to a particular moment in the flow of time. The process of memory involves the brain's ability to store information and recall it later. But how exactly do these memories shape our experience of time? And how does our brain organize these memories in a way that allows us to experience time as a flowing, linear progression? Psychologists have long explored the way we remember and how this relates to our sense of time. One useful distinction that has been made is between short-term memory and long-term memory. Short-term memory, or working memory, holds information for a brief period, often just seconds or minutes, allowing us to keep track of things we need in the moment, like remembering a phone number long enough to dial it, or keeping track of a conversation. Long-term memory, on the other hand, is the more enduring storehouse, where events, facts, and experiences are preserved for longer periods, ranging from hours to a lifetime. Short-term memory is more transient. It serves as a temporary workspace for information that is actively being processed. In contrast, long-term memory stores those experiences and facts that are deemed important enough to be kept for later use. This division between short-term and long-term memory is crucial for how we perceive time. Short-term memory helps us keep track of the present, while long-term memory helps us anchor ourselves to the past and give meaning to our experiences. But how does the brain decide what gets stored in long-term memory? Not everything we experience makes its way into long-term memory. Many events, especially those that are less significant, are filtered out. Our brains seem to prioritize memories that are either emotionally charged or have strong significance to our sense of identity. For instance, you might clearly remember a pivotal moment in your life, such as a wedding or the birth of a child, because these events are rich with emotional and personal significance. These experiences are embedded deeply in your memory, and they help anchor your sense of time, marking where you were at specific points in your life. Interestingly, the brain's ability to store and recall memories is not always perfect. Over time, some memories can fade and others can become distorted. This brings us to the intriguing connection between memory and the perception of time's passage. Our ability to recall events in sequence is a key aspect of our sense of time. When we retrieve a memory, we not only recall the event itself, but also the context in which it occurred, giving us a sense of when it happened. The more memories we accumulate, the stronger our perception of time's flow becomes, as we have a continuous personal record of events that have unfolded. However, disruptions in memory can also disrupt our sense of time. For example, as people age, their memory can begin to decline. Dementia, such as Alzheimer's disease, is particularly known for its impact on memory. Individuals suffering from dementia often struggle to recall even recent events, and their memories of the past may become increasingly fragmented. This can lead to a disjointed experience of time. For someone with memory impairment, the linear progression of time can become less clear. Events may no longer be stored in a coherent chronological sequence, and the sense of continuity that we take for granted may begin to unravel. This shift in how we perceive time as a result of memory disruption is especially significant when we consider how the brain organizes experiences. When memory is functioning properly, the events of our lives are stored in a sequence, giving us a clear sense of past, present, and future. But when memory becomes impaired, the flow of time itself can start to feel less certain. A person with dementia, for example, might not be able to distinguish between yesterday and 10 years ago. For them, time may seem less like a linear progression, and more like a series of isolated moments, which they struggle to connect. This disruption in memory can also alter their understanding of the passage of time, making the world feel more confusing and disconnected. The biological mechanisms behind memory are also fascinating when we consider their role in shaping time's one-way nature. Memory formation is closely tied to the hippocampus, a small, seahorse-shaped structure in the brain. The hippocampus helps encode new memories and connects them to existing ones, allowing us to build a coherent narrative of our past. When we remember something, the hippocampus reactivates the neurons that were involved in the original experience, creating a mental reconstruction of that moment in time. This process is not always perfect. Memories can be altered or faded, but it is essential for our experience of time as something continuous and flowing forward. But what happens when these mechanisms go awry? When memory fails, not only do we lose access to the past, but we also lose our sense of how the present connects to it. Time, in a sense, becomes disembodied, no longer anchored to the flow of experience. People with certain types of amnesia, for instance, may not be able to remember anything that happened before a specific point in time. This creates a break in the continuity of time, making their experience of the present seem disconnected from any past events. Their internal sense of time might be distorted, as they can't fully relate to past experiences or plan for future ones in the same way that someone with intact memory can. As we dive deeper into the connection between memory and time, we see that time is not just an abstract concept. It's something that is deeply embedded in the brain's ability to process and store information. Without memory, our experience of time would be chaotic, lacking any coherent structure or progression. Memory provides the foundation for our sense of time's flow, organizing the events of our lives into a sequence that allows us to make sense of where we've been and where we're going. What's truly fascinating about this relationship is how memory and time interact in shaping our identities. Our sense of self is, in many ways, a product of the memories we accumulate. The person you are today is built upon the experiences you've had, and those experiences are stored as memories that link your past to your present. This personal narrative gives us a sense of continuity over time. When we look back at our lives, we don't just see a series of disconnected events. We see a coherent story that gives us meaning and direction. This process is crucial for our understanding of the arrow of time, as it connects our subjective experience of time with the objective passage of time. The one-way nature of time, where events move forward, from past to present to future, mirrors our experience of how memory works. We can't retrieve the future, nor can we return to the past. We can only move forward in time, storing memories as we go, each one forming a building block for our future experiences. In the end, the connection between memory and time is one of the most intimate and profound relationships in our lives. Time is not just a series of ticking moments. It's a continuous flow of experiences, each one stored in our memory, giving us a sense of who we are and where we've been. Memory allows us to experience time as a coherent, linear progression, and disruptions to memory remind us just how essential that continuity is to our understanding of the world around us. Time, in this sense, is not just something we measure, it's something we live. Time is often treated as a fundamental, universal force, a constant that governs the natural world and the universe at large. It's measured by clocks, experienced by humans, and woven into the fabric of our daily lives. But in modern philosophy, time has been viewed through a different lens, one that challenges the traditional scientific understanding and offers alternative conceptualizations of what time really is. Philosophers have explored time not only as a physical phenomenon, but also as something shaped by human perception, society, and even the power structures that govern our lives. One of the most intriguing perspectives on time comes from Michel Foucault, a 20th century philosopher who focused on how time is organized within society. Foucault proposed the concept of social time, arguing that time is not something that simply exists in nature, but rather it is a construct shaped by the power dynamics of society. In his view, the way we experience time, the way it is measured, segmented, and lived, has everything to do with the structures of power that organize our social systems. The clock, for example, is not just a neutral tool for measuring time. It has been historically used to regulate the lives of individuals, dictating when we work, when we rest, and when we sleep. The rise of industrialization and capitalism, Foucault argued, led to the creation of a system of timekeeping that was used to control individuals, essentially transforming time into a tool of power. Foucault's ideas about time suggest that how we experience time is not merely an individual or natural experience, but one deeply embedded in societal structures. The very notion of time as a uniform, ever-ticking force that governs our lives can be seen as a social construct, a product of the way power has shaped our institutions, from schools and workplaces to governments and industries. Time, in this sense, is less about the objective passage of moments, and more about how society organizes and controls the flow of our daily lives. But time can be understood differently too. Henri Bergson, a French philosopher active in the late 19th and early 20th centuries, had a very different view of time. For Bergson, time is not something that can be measured by clocks or reduced to a series of discrete moments. Instead, he introduced the concept of la durée, or duration, which is a form of time that is qualitative rather than quantitative. According to Bergson, the time we experience in our everyday lives is not simply a sequence of mechanical, measurable moments. Instead, it is a continuous, flowing experience, one that cannot be fully captured by the rigid ticking of a clock. La durée for Bergson is the lived experience of time, the time we feel in our hearts, in our memories, and in our consciousness. Bergson argued that the more we focus on measuring time and breaking it down into discrete units, the more we lose touch with its true nature. To truly understand time, we must abandon the mechanical scientific model of time and embrace its fluid, experiential quality. This view stands in stark contrast to the scientific perspective of time, where it is treated as an abstract, quantifiable dimension. For Bergson, time isn't just something we observe from the outside, it's something we live and experience from the inside. His philosophy suggests that time is deeply connected to consciousness, to perception, and to the way we process and experience the world. It's a personal, subjective phenomenon that can't be entirely captured by the ticking of a clock. This perspective on time also connects to the philosophy of consciousness, where the flow of time is tied to our internal mental states. When we recall memories, for example, we don't experience them as isolated events on a timeline. Instead, we experience them as a continuous stream, woven together by our subjective experience. This flowing subjective sense of time is very much in line with Bergson's ideas of la durée, where time is a continuous unfolding experience, rather than a rigidly segmented sequence. Bergson's ideas on time also intersect with the work of Kurt Gödel, a renowned mathematician and logician whose work on the nature of time has had a profound impact on the way we think about the structure of the universe. Gödel's work on relativity and the nature of time provided the groundwork for understanding how time might function in a non-linear way, even in the context of general relativity. Gödel famously proposed that time loops, or closed time-like curves, could exist within the framework of relativity, allowing for the possibility of time travel and paradoxical scenarios. In his model, time does not follow a simple, forward-moving arrow, but instead could loop back on itself, creating a closed cycle. This idea of time as a loop, one where the future could potentially connect with the past, challenges the conventional view of time as linear and unidirectional. If closed time-like curves exist, time might not be a one-way street, but rather a more intricate structure that could loop back on itself. This idea has profound implications for how we think about causality, free will, and the flow of time. If time could loop back, the boundaries between past, present, and future would become blurred, leading to a far more complex understanding of how time operates. In considering these more philosophical views of time, we begin to see that time may not be the simple, external force that we often assume it to be. It may not be just something that ticks away, objectively and independently of us. Instead, time could be deeply intertwined with consciousness, experience, and the structures of society. It could be subjective, qualitative, and even paradoxical, shaped not just by the clock, but by the way we experience and interpret the world. This brings us to Immanuel Kant, a philosopher whose ideas about time continue to influence how we think about the relationship between time and perception. Kant argued that time, along with space, is a form of intuition, a basic framework that structures all human experience. For Kant, time is not something that exists independently of us, but rather something we impose on the world in order to make sense of it. Time is a lens through which we perceive events, and without this lens, we would have no coherent understanding of the world. Kant's theory suggests that time, in a sense, is not a physical property of the universe, but a mental construct, a necessary framework for human experience. This resonates with Bergson's ideas of la durée, where time is not just a sequence of moments, but a way of understanding and experiencing the world. In this view, time is not an absolute external force, but something that is experienced differently, depending on our perception, our culture, and our consciousness. The different ways philosophers have conceptualized time, whether as a social construct, a subjective experience, or a mental framework, highlight the rich complexity of the concept. Time is not just a simple dimension that we measure and observe. It is something that shapes our very understanding of the world. It is intertwined with how we remember, how we experience the present, and how we anticipate the future. Time, in all its forms, is as much about perception as it is about physical reality, offering a rich tapestry of ideas that challenge and deepen our understanding of what time really is. In the end, these philosophical perspectives suggest that time is not just a ticking clock, but a deeply personal and subjective experience. It's something that we construct in our minds, something that is shaped by our culture, our consciousness, and the way we interact with the world. Time, in its most profound sense, is not merely a force that governs the universe. It is also a force that governs our perception of existence itself. Time is a fundamental part of our lives, yet it is experienced differently by different individuals. While time seems to flow at a steady, unchanging pace, our perception of it is anything but uniform. Time can feel slow, fast, or even distorted, depending on our mental state, the circumstances we find ourselves in, and the way our brains process the passage of time. Understanding how the brain constructs our perception of time and why it can be so malleable is a fascinating area of study that bridges psychology, neuroscience, and philosophy. One of the key insights into how we experience time comes from the work of Daniel Kahneman, a psychologist who won the Nobel Prize in Economics for his groundbreaking research on cognitive biases and decision-making. Kahneman's research reveals that our perception of time is often distorted by our mental state and emotional experiences. For example, when people are engaged in activities they enjoy, time tends to feel like it passes quickly. Conversely, when we are bored, anxious, or stressed, time can feel like it stretches on endlessly. This phenomenon can be explained in part by what Kahneman refers to as the experiencing self and the remembering self. The experiencing self is the part of us that lives in the moment, feeling the passage of time as it happens. The remembering self, on the other hand, is the part of us that looks back at experiences and creates a narrative from them. Interestingly, the two selves do not always agree. The experiencing self might feel that time is dragging during a difficult task, while the remembering self might perceive the same experience as having passed quickly, especially if it ends on a high note. This difference in perspective can influence how we feel about time's passage, and it plays a significant role in how we remember our lives. Kahneman's research shows that the peak of an experience and its end have a disproportionate influence on our memory of it, affecting our sense of how long or short an event felt. The experience of time is also deeply influenced by our brain's cognitive processes. When we are in a state of flow, a term coined by psychologist Mihaly Csikszentmihalyi, time seems to disappear. Flow occurs when we are fully immersed in an activity, whether it's working on a creative project, playing a sport, or solving a challenging problem. In this state, our attention is so focused that we lose track of time entirely. Time can fly by, and hours can feel like minutes. This is because, in a flow state, the brain is functioning at its optimal level of focus and engagement, bypassing the usual markers we use to measure time. Instead of thinking about the past or future, we are completely absorbed in the present moment. In contrast, stress and anxiety can make time feel as though it's moving at a snail's pace. When we're under pressure, the brain becomes hyper-focused on the threat or discomfort, amplifying our sense of time passing slowly. This is particularly evident in situations like waiting for an important call or enduring a stressful event, where minutes can feel like hours. Stress hormones, such as cortisol, may contribute to this altered perception by hijacking our mental focus and intensifying our experience of time. In these moments, time doesn't feel like a smooth, continuous flow. It feels fractured, stretched, and unbearably slow. Beyond individual psychological states, time is also shaped by the phenomenology of time, a field of philosophy introduced by Edmund Husserl. Husserl's ideas on time differ significantly from the scientific perspective of time as a measurable quantity. He argued that time should be understood as the lived experience of becoming, not simply as a metric of change. According to Husserl, our experience of time is not just a sequence of past, present, and future moments, but an ongoing process of becoming. Time is something we feel and experience as it unfolds, not something we simply measure. This concept challenges the notion that time is simply an abstract, objective measurement of the world. Instead, it's something we engage with in the course of our lived experiences, shaping how we perceive ourselves and our surroundings. Husserl's phenomenology emphasizes that time is deeply connected to our sense of self and the continuity of our experiences. When we look back on our lives, we don't just recall events as isolated moments in time. Instead, we remember them as part of a flowing, continuous narrative that gives us a sense of personal identity. This continuity is made possible by our experience of time as something that we live rather than something we merely measure. This perspective suggests that time, at least in part, is subjective, shaped by the way we perceive and experience it, rather than simply being a consistent external force. Another factor that influences how we experience time is culture. Different cultures have distinct attitudes toward time, and these cultural differences can significantly affect how individuals perceive and interact with time. Edward T. Hall, an anthropologist, categorized cultures as either high context or low context in terms of their approach to time. High context cultures, such as those in many Asian and Latin American countries, tend to emphasize the quality of time, valuing relationships, flexibility, and a more fluid, less structured approach to time. In these cultures, time is often seen as something that should be experienced organically, and punctuality may not be as rigidly enforced. On the other hand, low-context cultures, such as those in many Western countries, tend to view time as a quantifiable resource, something that must be managed and scheduled carefully. In these societies, time is more likely to be structured, and efficiency and punctuality are highly valued. This cultural difference can lead to vastly different perceptions of time. For example, in high-context cultures, events may feel less rushed, as there is a greater emphasis on the present moment and relationships. In low-context cultures, time might feel more hurried or fragmented, with a greater emphasis on getting things done quickly and efficiently. Interestingly, time perception can also be influenced by practices such as mindfulness and meditation, which have become increasingly popular in recent years. These practices help individuals slow down and become more present in the moment, shifting the way they experience time. Mindfulness encourages people to focus on the here and now, rather than being preoccupied with the past or future. By learning to be more aware of the present moment, individuals can cultivate a deeper connection to time, helping them feel less rushed or stressed. In fact, mindfulness practices have been shown to slow down the perception of time, allowing people to feel more grounded and present. On the flip side, meditation, especially practices that involve deep focus or concentration, can also affect the perception of time. During meditation, time may seem to stretch or expand as the individual becomes less aware of the passing minutes and more immersed in the present moment. In some cases, this can create a sense of timelessness, where the individual is no longer aware of the external measurement of time. Meditation helps reframe the experience of time from something that is external and limiting to something that is fluid and expansive, providing an entirely new way of interacting with the world. These various factors, psychological states, cultural influences, and mindfulness practices demonstrate that time is not experienced in a singular, objective way. Time is a deeply personal, subjective experience that can be altered and shaped by the way we engage with it. Whether we are in a state of flow, stressed out by anxiety, or practicing mindfulness, the way we perceive time is constantly shifting. Time, in many ways, is as much about our perception of it as it is about the external ticking clock, and as we continue to explore the science and philosophy of time, it's clear that our understanding of time, both individually and collectively, is far more complex and fluid than we might have once thought. The mysteries of time take on a new dimension when we enter the realm of quantum mechanics, a world where the classical laws of time and space break down in ways that challenge everything we think we know about the universe. The conventional understanding of time as a linear progression, a steady flow from past to present to future, simply doesn't hold in the quantum realm. Here, time behaves in ways that seem utterly counterintuitive, opening up fascinating possibilities that blur the boundaries between reality and theory. One of the most intriguing theories about time in the quantum world comes from David Bohm, a physicist known for his work on quantum theory and his interpretation of the universe as a whole. Bohm proposed the idea of a holonomic universe, where time is not just a straightforward flow of moments but a latent order, a deeper underlying structure that only reveals itself as the universe unfolds. In this view, time itself isn't an absolute, unchanging force but something that emerges from the interactions of fundamental processes. Time, according to Bohm, is a dynamic feature of the universe, one that becomes apparent as the universe develops, much like how the colours and patterns on the surface of a painting slowly come into focus as the artist works. This holonomic model suggests that time is not fundamental in the traditional sense. It's not something that exists independently of the universe, ticking away in the background. Rather, time is a product of the deeper, more fundamental forces that govern the universe. Just as the underlying quantum fields give rise to particles and energy, these same fields give rise to the experience of time. Time, in this sense, is an emergent phenomenon, a result of the unfolding universe rather than a constant that simply exists. The latent order Bohm described might be a deeper pattern that ties together all of reality, with time being a way to express this pattern at the level we experience. But Bohm's ideas are just the tip of the iceberg. Another visionary thinker who reimagined the structure of time was Roger Penrose, whose theories on twistors offer a radically different perspective on space-time. Penrose introduced twistors as a new mathematical approach to understanding the structure of space-time, particularly within the context of quantum mechanics. Twistors aren't just a theoretical construct, they represent a new way of thinking about how time and space are related, suggesting that time may not be a fundamental feature of the universe. Instead, time could be a higher-level manifestation of more complex relationships between fundamental physical entities. The key idea behind Penrose's theory of twistors is that space-time can be understood not as a flat, continuous entity, but as a more complex structure that exists at multiple levels. In this framework, time is not a fixed, linear force that operates on its own but is instead a consequence of how objects and forces interact at a deeper level. Time, in Penrose's view, is a result of these interactions, an emergent feature that is tied to the geometry of space-time, rather than something that exists independently. Penrose's twistors are a mathematical tool that allows physicists to explore these deeper relationships between time, space, and quantum mechanics. By using twistors, it becomes possible to understand how time might not be as fundamental as we once thought, but rather a product of the way the universe's underlying structure behaves. Time, in this model, is something we perceive because of the patterns and relationships that exist between particles and forces, not something that exists separately from the world around us. This leads to a more fundamental question. If time isn't a fundamental property of the universe, what is the nature of the universe itself? John Wheeler, one of the most influential physicists of the 20th century, proposed a radical answer to this question with his idea of the participatory universe. According to Wheeler, the universe is not something that simply exists independently of us, with time unfolding according to fixed laws. Instead, he argued that observers, in other words, conscious beings like us, actually play a key role in determining the flow of time and the nature of physical reality. Wheeler's participatory universe suggests that reality is not fixed. It is created through the interaction of observers with the universe. In this model, time itself may not be a pre-existing feature of the universe, but rather something that is shaped and influenced by observation. The universe, according to this idea, doesn't just unfold passively, it is actively influenced by those who perceive it. In a way, the act of observation shapes the passage of time and the unfolding of events, creating a universe that exists in a constant state of co-creation. The flow of time is not a passive experience, but a dynamic process that is deeply connected to the act of observing and interacting with the universe. This idea ties into the quantum mechanics interpretation of reality, where observation plays a crucial role in determining the state of a system. In quantum mechanics, particles exist in a superposition of multiple states until they are observed, at which point they collapse into one definite state. Wheeler's theory suggests that this principle of quantum mechanics extends beyond individual particles to the universe as a whole. Time itself, in this model, is not an independent force but something that is influenced by our perception and the way we engage with the world around us. This brings us to another key concept in modern physics, string theory, and the contributions of Edward Witten, one of the leading figures in the field. String theory suggests that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings. These strings exist in higher dimensions, many of which are beyond our ability to perceive. According to Witten and other string theorists, these extra dimensions may offer insights into the quantum fabric of time, how time behaves at the most fundamental level. In string theory, time is not a separate dimension, but something that is woven into the fabric of the universe. Much like the other fundamental forces, the interactions between these vibrating strings give rise to the particles, forces, and even time itself. String theory's perspective on time suggests that time could be much more flexible and interconnected with the fundamental forces of nature than we've traditionally thought. Time might not be a simple linear flow, but could be a more intricate, multi-dimensional feature of the universe that is tied to the behavior of the strings and the extra dimensions that govern them. Finally, there's the many worlds interpretation of quantum mechanics, which suggests that time may not be the same in every possible outcome of a quantum event. According to the many worlds theory, every time a quantum event occurs, the universe splits, creating parallel realities in which each possible outcome of the event is realized. This means that time doesn't follow a single, unidirectional flow. Rather, it unfolds differently in each possible world. In some universes, time may move forward as we know it, while in others, time could unfold in completely different ways, depending on the specific quantum outcomes that occur. The many worlds interpretation challenges the idea of time as a singular linear progression. Instead, it suggests that time could be part of a branching, multidimensional structure in which every possible outcome of a quantum event creates a new timeline, with its own unfolding of time. This perspective on time expands our understanding of reality, showing that time might not be a universal constant, but something that unfolds in a vast, complex web of possibilities. All of these ideas, from Bohm's latent order to Penrose's twistors, Wheeler's participatory universe, Witten's string theory, and the many worlds interpretation, suggest that time, far from being a simple, unidirectional force, might be a much more complex, multifaceted phenomenon. Time could emerge from the deeper structures of the universe, shaped by our observations, the behavior of quantum particles, and the very fabric of space-time itself. As we continue to explore these theories, it becomes clear that our understanding of time is far from complete, and the true nature of time may still be one of the greatest mysteries of the universe. The idea of time travel has fascinated humanity for centuries. It's a concept that has been explored in countless works of science fiction, whether it's through a time machine, like in H.G. Wells' The Time Machine, or in more modern interpretations like the Back to the Future films. In these stories, time travel is often portrayed as a thrilling adventure, allowing characters to journey through the past or future, change events, and explore alternate timelines. But as intriguing as time travel is in fiction, it also raises profound questions about the nature of time itself, causality, and the very fabric of the universe. The question is, can time travel be more than just a fantasy? Is it possible according to the laws of physics? Interestingly, general relativity, the theory developed by Albert Einstein to describe the force of gravity, suggests that time travel may not be entirely out of the realm of possibility, at least in theory. According to general relativity, space-time, the fabric of space and time, is not a rigid backdrop, but something that can be warped and curved by massive objects like stars and black holes. This means that time itself can be influenced by the shape of space-time, which opens up the potential for some very strange possibilities. One of the most well-known theoretical concepts related to time travel is the idea of a wormhole. Wormholes are hypothetical passages through space-time that connect distant points in the universe, forming a sort of shortcut between them. Imagine folding a piece of paper so that two distant points on it are aligned. A wormhole, in this analogy, would be the hole that connects the 2 points. If such a structure existed, it could allow an object, or theoretically a person, to travel between the 2 points instantaneously, bypassing the vast distances of space. Wormholes, however, are not just theoretical shortcuts through space. If they exist, they might also connect different points in time. This means that, if a wormhole could be stabilized, it might allow for time travel, not just across space but also across time. One end of the wormhole could be located in the present, and the other in the past or future. This could theoretically allow someone to travel backward or forward in time by entering the wormhole and emerging at a different moment in history. But there are significant challenges to this idea. For one, wormholes are purely hypothetical at this point. No one has ever observed one in the wild, and creating a stable wormhole, assuming it could exist, would likely require exotic forms of matter or energy that we have yet to discover. Another intriguing possibility in the realm of time travel comes from closed time-like curves, CTCs, a concept that arises from the equations of general relativity. CTCs are solutions to the equations of spacetime that allow for paths that loop back on themselves, essentially creating a loop in time. This would mean that an object could travel along this curve and eventually return to its own past, effectively traveling backward in time. CTCs are mathematically consistent and do not violate the laws of general relativity. However, they are purely theoretical, and it's unclear whether such curves actually exist in the real universe or if they could be created in any practical way. The concept of closed time-like curves raises interesting philosophical and logical questions, especially when we consider the implications of time travel on causality. For example, the grandfather paradox is a famous thought experiment that explores what happens if you travel back in time and alter an event in the past. Imagine you go back and accidentally prevent your grandfather from meeting your grandmother. If that happens, your parent would never be born, and as a result you would never exist. But if you never existed, how could you have gone back in time to prevent your grandfather from meeting your grandmother in the first place? This creates a logical paradox, a situation where cause and effect seem to break down completely. The grandfather paradox highlights a critical issue with time travel, the causal loop. When time travel allows you to change the past, it raises the question of how time can maintain its one-way flow. If time is fundamentally structured to move from the past to the future, how can a person travel backward and alter events in a way that creates contradictions? The grandfather paradox isn't just a philosophical curiosity. It's a real problem that physicists must confront when considering whether time travel is truly possible. Despite these challenges, some physicists have proposed potential solutions to the paradox. One suggestion is the idea of consistency constraints, the notion that the laws of physics somehow prevent paradoxical events from occurring. According to this view, even if time travel were possible, events in the past would be constrained in such a way that any attempt to change them would be thwarted. In other words, the universe would self-correct to ensure that contradictions don't arise. This idea is often referred to as the Novikov self-consistency principle, which suggests that time travel is possible, but only if events unfold in a way that is consistent with the timeline we know. Another solution to the paradox comes from the many worlds interpretation of quantum mechanics, which suggests that every time a quantum event occurs, the universe splits into multiple parallel realities. In the context of time travel, this idea could mean that when you travel back in time and make a change, you don't alter your own timeline. Instead, you create a new timeline, one that runs parallel to your original timeline. This means that the changes you make in the past don't affect your original reality, preventing the grandfather paradox from occurring. While the many worlds interpretation is still speculative and has not been definitively proven, it provides an interesting solution to the problems posed by time travel. If time travel were ever to become possible, it would also have profound implications for the directionality of time. The arrow of time, which is the concept that time flows in one direction, from the past toward the future, is deeply tied to the second law of thermodynamics, which governs the increase of entropy, or disorder, in the universe. The forward flow of time is associated with the increase of entropy, but if time travel allowed us to move backward, it could theoretically reverse this process, creating a situation where events lose their directionality. This is why backward time travel is so conceptually challenging. It would essentially mean reversing the fundamental process of entropy, which is thought to be a one-way, irreversible force in the universe. The challenge of time travel is not just theoretical. It touches on some of the deepest questions about the nature of time itself. Can time be reversed, or is it always destined to flow forward? Can the past truly be altered, or are we bound by a fixed timeline? These are questions that science fiction has explored for years, but they also remain at the forefront of modern physics. Time travel presents a fascinating conceptual challenge, but it also forces us to confront the nature of reality, causality, and the flow of time. Whether or not time travel will ever be possible, the questions it raises will continue to shape our understanding of the universe for generations to come. Time is a concept that touches everything in the universe, but it is experienced in very different ways by living organisms. While humans have an intuitive grasp of time, shaped by our daily routines, there are other creatures whose experience of time may be vastly different, sometimes more sensitive, sometimes less. Time perception is deeply woven into the fabric of life, and it's shaped by biological clocks, environmental cues, and the very mechanisms that drive life processes. One of the most fascinating aspects of how living beings perceive time is through the use of biological clocks. In humans and animals, these clocks help regulate vital functions and behaviors, often on a daily or seasonal basis. One of the most well-known biological clocks is the circadian rhythm, which operates on a roughly 24-hour cycle. The word circadian comes from the Latin circa diem, meaning around a day. This internal clock controls our sleep-wake cycles, body temperature, hormone release, and many other processes that keep us functioning in sync with the planet's day-night cycle. Circadian rhythms are regulated by an area of the brain called the suprachiasmatic nucleus, SCN, located in the hypothalamus. The SCN acts like a master clock, receiving light signals from the eyes to adjust the body's rhythms accordingly. This synchronization with the Earth's rotation is crucial for most living organisms. For humans, a disruption in our circadian rhythm, such as from jet lag or shift work, can cause a variety of issues, including fatigue, difficulty concentrating, and even increased risk for certain diseases. But it's not just humans that rely on circadian rhythms, many animals do as well. Migratory birds, for instance, use their internal clocks to navigate long distances, adjusting their behavior based on the time of day or the season. Circadian rhythms are just one example of how living beings perceive time. Many organisms also possess clocks that help them track longer cycles, such as the seasonal rhythms of reproduction, hibernation, and migration. Some animals, like certain species of fish and amphibians, have circannual rhythms that regulate seasonal behavior, such as breeding or entering dormancy. These biological timekeepers are essential for organisms that need to synchronize their behaviors with the changing environment. The way time is measured within living systems goes beyond just the daily cycle of waking and sleeping. It's also deeply tied to processes like aging and metabolism. From a biological perspective, aging can be thought of as the gradual accumulation of damage to cells and tissues over time. This process, while inevitable, is influenced by our biology and how our cells and organs manage time at the molecular level. Cells constantly engage in metabolic processes, converting energy from food into fuel for the body, but these processes also produce byproducts like free radicals that can cause damage over time. This damage in turn contributes to aging. Interestingly, our metabolism itself operates on time-sensitive cycles. For example, the body's metabolism speeds up during the daytime when we're active and slows down at night during sleep. The ability of the body to manage and balance these cycles is essential for maintaining health. As we age, the efficiency of these biological clocks and metabolic processes can decline, contributing to the effects of aging. When we think about how living systems interact with time, we must also consider the work of Francis Crick, best known for his role in discovering the structure of DNA. Later in his career, Crick turned his attention to the brain and its function in processing time. Crick proposed that our experience of time, including our sense of present moment awareness, could be deeply tied to brain function. Specifically, he believed that the brain's ability to measure time was connected to its capacity to process and interpret sensory information. Our awareness of the passage of time might be a fundamental aspect of consciousness, helping us create a continuous sense of self and a coherent perception of the world. In Crick's view, the brain doesn't just perceive the present, it also helps us make predictions about the future based on the past. This ability to track time allows organisms to react appropriately to changes in their environment. The brain processes these time-based cues, adjusting behavior to the changing rhythms of the world around us. In this sense, time perception is a dynamic, adaptive process that plays a critical role in survival. Time is not just experienced in humans or animals with brains, though. Evolutionary theory suggests that the need to measure time is deeply embedded in the biological design of many species. Time-sensitive mechanisms evolved as part of the survival strategies of organisms. For instance, the development of seasonal behaviors like migration, hibernation, or reproduction is often closely linked to internal timekeeping mechanisms that have evolved over millennia. These rhythms are crucial because they allow organisms to anticipate and adapt to changes in their environment, ensuring that they are ready for events like seasonal food shortages or changes in temperature. Without these biological clocks, organisms would struggle to survive in the face of predictable, cyclical changes in the environment. The evolution of time-sensitive systems also extends to how species synchronize their behavior. Take, for example, courtship behaviors in many animals, where reproduction is timed with specific environmental cues, like the availability of food or the onset of warmer weather. These reproductive cycles, which are often linked to circadian rhythms, ensure that offspring are born at the most advantageous time for survival. In this sense, time becomes a central organizing principle for life itself, shaping when and how organisms perform key behaviors that are essential for their survival and continuation of the species. There is also the fascinating question of how time is perceived by organisms with very different biology from our own. For example, how do insects or birds experience time, considering they have faster metabolic rates than humans? It turns out that many species perceive time in a way that is directly tied to their biology. Insects like fruit flies have much faster brain processing speeds than humans, allowing them to perceive time in finer increments. As a result, their perception of time is much quicker, and they experience the world at a different pace. For these creatures, time may feel like it's moving more slowly, as they process and react to stimuli more quickly than we can. In contrast, creatures with much slower metabolic rates, like some species of tortoises, might experience time in a much more leisurely way, processing sensory information at a slower rate. These differences in time perception can have profound effects on how organisms interact with their environment and how they evolve to cope with it. Time, in this sense, is not just a universal constant. It's something that organisms experience and adapt to according to their specific needs and biology. This diversity in time perception also raises interesting questions about how consciousness and awareness of time might differ between species. While humans have a highly developed sense of time, able to anticipate the future and remember the past with remarkable precision, other animals may experience time in a more immediate, present-focused way. In some species, time may be experienced less as a linear progression and more as a series of interconnected moments, shaped by the rhythms of their biological clocks and the demands of their environment. Ultimately, the biological perception of time underscores just how deeply time is embedded in the fabric of life. From the circadian rhythms that help us wake up in the morning to the complex processes that govern metabolism, aging, and behavior, time is not just a backdrop to life. It is intricately tied to how living beings function, evolve, and interact with the world. Time, in a biological sense, is far from a simple abstract concept. It's a dynamic force, constantly shaping and guiding life at every level, from the smallest organism to the most complex systems of thought. The concept of time has long been an intriguing and often elusive idea, but it becomes even more complex when we begin to consider the possibility of the multiverse. The idea that our universe might not be the only one, but rather one of many, each with its own unique properties and laws. If the multiverse theory holds any truth, it could have profound implications for our understanding of time, suggesting that time is not a universal constant, but could vary across different universes. The idea of parallel universes, with potentially different timelines, challenges traditional concepts of time and invites us to think beyond the boundaries of our own reality. One of the most well-known theories about the multiverse comes from Andrei Linde, a physicist who developed the concept of eternal inflation. Linde's theory proposes that the universe began with a period of rapid expansion known as inflation, which occurred shortly after the Big Bang. According to the theory, inflation didn't stop at a single point but rather continues endlessly, creating an infinite number of pocket universes. Each of these pocket universes is essentially a separate bubble within the larger multiverse, with its own set of physical laws and properties. These universes are constantly being spawned, with each new pocket universe expanding from the fabric of the larger multiverse. From the perspective of time, the implications of eternal inflation are profound. If the multiverse is constantly generating new universes, each with its own distinct timeline, then time is no longer a simple linear progression that applies universally. Instead, time could behave differently in each universe, depending on the specific conditions within that universe. In some universes, time might flow in a way that is similar to our own, with a steady, forward-moving progression. In others, time could take on entirely different properties, with different rates of flow or even alternative directions of time. This idea radically alters our understanding of time's nature. Instead of thinking of time as an absolute one-size-fits-all feature of the universe, Linda's theory suggests that time might be a flexible, dynamic property that depends on the specific rules and conditions of each individual universe. Time could be experienced in countless ways across the multiverse, with each pocket universe having its own version of time, shaped by its particular physical laws. Another thought-provoking approach to the multiverse and time comes from Max Tegmark, a physicist known for his mathematical universe hypothesis. Tegmark's theory proposes that the universe is not just governed by mathematical laws, but that mathematics itself is the very fabric of reality. According to this hypothesis, the multiverse consists not only of parallel universes with different physical laws, but also of different mathematical structures, each of which corresponds to a different set of physical realities. These mathematical structures are, in essence, the blueprints of each universe, and within each structure, different timelines could exist, each with its own version of time. If time is a product of the mathematical structure of each universe, then time might not be the same in every universe. In one mathematical structure, time might progress in a linear fashion, just as we experience it in our universe. In another, time might be cyclical, or might not even exist in the way we understand it. For example, in some universes time might not have a clear direction at all, or might be experienced as a static dimension, with no progression from past to future. Tegmark's theory suggests that the variety of mathematical structures in the multiverse could give rise to a wide range of possible timelines, some of which might be completely alien to our own experience of time. The idea that time is linked to the underlying mathematical structure of the universe challenges the traditional view of time as a fundamental, objective feature of reality. In Tegmark's multiverse, time is not an absolute constant, but a product of the specific mathematical framework that governs each universe. This means that time, in the context of the multiverse, could be just one possible way of experiencing reality, and there could be other forms of time that we cannot even begin to imagine. The multiverse theory also raises the possibility that the directionality of time, the fact that time flows in one direction, from the past toward the future, might not be the same in every universe. In our universe, the arrow of time is tied to the second law of thermodynamics, which states that entropy, or disorder, always increases over time. As entropy increases, time moves forward in one direction, creating a clear distinction between past, present, and future. But in other universes, the laws of thermodynamics might be different, leading to alternate forms of time that don't follow the same arrow. If time is not constrained by the second law in these universes, then it might not have the same forward progression that we experience in our universe. This brings us to a radical idea proposed by John Wheeler, one of the pioneers of quantum mechanics, who introduced the concept of the participatory universe. Wheeler suggested that the universe is not something that exists independently of us, but rather it is shaped by the observers, the conscious beings who interact with it. In Wheeler's view, time is not a passive backdrop to the universe's events, but something that is actively influenced by the act of observation. The flow of time itself might depend on who is observing it and how they are perceiving it. If this is true, then time could be fundamentally different in different universes, depending on the observers and their interactions with the world around them. In a participatory universe, the act of observing the universe could create time, or, at the very least, influence its direction. The future might not be a fixed, predetermined path, but one that is shaped by the choices and actions of conscious beings. This theory suggests that time is not just an external force that exists independently of us, but something that is deeply connected to consciousness and observation. The idea of a multiverse and the flexible nature of time it implies raises deep philosophical and scientific questions about the nature of reality itself. If time can vary across different universes, what does this mean for our understanding of causality, free will, and determinism? Is time an objective feature of the universe, or is it a subjective experience shaped by the interactions between observers and the universe they inhabit? And if time is not a universal constant, but something that depends on the specific conditions of each universe, what does that tell us about the fundamental nature of reality? One of the most fascinating implications of the multiverse theory is that it challenges the very concept of a singular, objective timeline. If multiple universes with different timelines exist, then the passage of time might not be as fixed or absolute as we have always assumed. Instead, time could be a dynamic, evolving feature of reality that varies depending on the universe, the observer, and the mathematical structure that governs the universe. In this view, time is not just a universal truth, but a malleable, flexible aspect of reality that could take on different forms across the multiverse. The multiverse theory opens up a whole new way of thinking about time. Instead of seeing it as a single, linear force that governs all of reality, we begin to see it as something that could vary widely, shaped by the universe's underlying structure. Time, as we understand it, may only be one version of time among many, and the multiverse may offer an infinite array of possibilities for how time can unfold. As we journeyed through the many facets of time in this exploration, we encountered a wide array of ideas, theories, and perspectives, some deeply rooted in physics, some emerging from philosophy, and some grounded in the lived human experience. We began with the fundamental concept of time's arrow, the one-way flow from past to present to future, a concept that seems so intuitive yet remains one of the greatest mysteries in both science and our daily lives. Time's direction, its passage, and its ultimate fate have long captured the attention of thinkers across disciplines, from the physical to the philosophical. In the realm of science, we looked at the theories that describe time as a fundamental aspect of the universe's functioning. General relativity, for instance, paints time as an integral part of space-time, something that can be warped and shaped by the presence of mass and gravity. Wormholes and closed time-like curves suggested that, theoretically, time travel could be possible, but only under very specific and mostly hypothetical conditions. Quantum mechanics added its own complexities, where time appears more fluid and malleable, with ideas like twistors, and the many worlds interpretation suggesting that time could vary dramatically across different realities and parallel universes. As we move from the scientific to the philosophical, time's nature became even more elusive. Thinkers like Henri Bergson argue that time, or la durée, was not something quantifiable or measured by clocks, but something that we live and experience, an ongoing flow of becoming. Philosophers like Immanuel Kant and Edmund Husserl emphasize that time is not an external force, but a frame of reference imposed by our minds, shaping our perception of reality and experience. Even Michel Foucault challenged the traditional view of time as an objective force, showing how time is often constructed and controlled by societal power structures, reflecting not just how we experience the world, but how we are made to experience it. In looking at living systems, we saw that time is not universally experienced. The biological rhythms that govern the life cycles of organisms, from circadian rhythms in humans to the seasonal clocks of animals, demonstrated how deeply ingrained time is in the fabric of life. Time is experienced differently by different species, influenced by metabolic rates, brain function, and evolutionary needs. Whether it's how we age, how we measure the passing of moments, or how our brains perceive time under different circumstances, living systems show us that time is far from a uniform experience. It is intimately tied to biology and consciousness itself. Perhaps most intriguingly, we ventured into the realm of theoretical physics, where time's nature and fate become tangled with the very structure of the universe. Concepts like eternal inflation and the multiverse suggest that time may not be a singular absolute force. In the multiverse, time might behave differently in each universe, influenced by the specific laws and conditions that govern that particular pocket of existence. Time might not be the same from one universe to another, stretching and bending in ways we can hardly fathom, giving rise to new questions about how time unfolds and whether it can even have a definitive end. From closed time-like curves to quantum entanglement, time may not be the orderly progression we perceive it to be, but something more complex, variable, and interconnected. As we reflect on these ideas, we begin to realize that time, in all its complexity, is not just a scientific or abstract problem. It is personal, experiential, and philosophical. It is something we live, something that defines our consciousness, shapes our existence, and marks the milestones of our lives. The forward flow of time, the arrow of time, might seem like an undeniable and straightforward concept, but when we delve deeper into its mysteries, we see how it interacts with the universe, with our minds, and with our perception of reality itself. It is not merely an external measurement, but a fundamental feature of existence, one that touches everything we know, yet remains elusive. We've come to understand that time's end, or perhaps its transformation, is not as certain as it might first appear. Whether it's the heat death of the universe, the cyclical nature of eternal inflation, or the speculative possibilities of time travel and alternate timelines, time seems to stretch far beyond our current understanding. It may not be as linear and irreversible as we've always thought, and it might even lead to new beginnings, as concepts like the Omega Point and the participatory universe suggest. But as we stand at the threshold of these fascinating ideas, one final question emerges. If time is indeed a fluid and evolving phenomenon, how do we, as individuals, experience its passage? Is our perception of time tied to the underlying nature of the universe, or is it something we too shape and create in the process of living? And perhaps most poignantly, as we look forward to the future, how will we continue to make sense of time's mysteries, not just as scientific puzzles, but as profound personal experiences that shape our lives? Time remains one of the greatest mysteries, an ever-unfolding question with no simple answers. And in this mystery, we find not only the ultimate challenge for science and philosophy, but also the key to understanding our place in the vast, intricate web of existence. So, as we continue to explore the depths of time, we are left with this question: is time's end truly the end, or could it be the beginning of something entirely new?